Get started. For those of you that don't know me, I'm Sterl Finney, the Executive Officer for Astronomy here. I was just a couple of years old when the events we're celebrating today were happening, so they didn't make a direct impression on me. But a few years later, one of my mother's neighbors gave me a book called Quasi-Stellar Objects by Burbage and Burbage, because she'd heard I was interested in astronomy. And I have to say I found it rather confusing. I was about 10 at the time, especially this part of the long parts about non-cosmological redshifts. But when I came to Caltech as an undergrad, Roger Blanford straightened me all out, and so ever since then I've understood how quasars worked. So we've heard this morning about the discoveries from Maarten and those who've worked on them. So we now turn to the current frontiers of the field, which you'll see the speakers are mostly a younger and more diverse set than the previous set. So we'll start off with Louis Ho of the Carnegie Observatories. Louis is a scientific grandchild of Wall, who we celebrated last night, and he'll tell us about black hole demographics.
Well, when quasars were discovered in 1963, I was minus 4 years old, so I'm extremely happy to be here. I'm honored, in fact, to be able to give a presentation at this important celebration of Maarten Schmidt and the amazing historical discovery of quasars, but also as an occasion to really celebrate the life and scientific achievements of Wal Sargent. We had a ceremony last night. Most of you perhaps aware that Wal has made seminal contributions to the very early efforts to dynamically detect black holes in elliptical galaxies such as M87. What may be less well known is that he's also made very important contributions to our overall understanding of the demographics of active galaxies and by implications AGNs, which really have foreshadowed many of the results to come in later decades. So with your indulgence, I'm going to give a bit of a historical overview of the Palomar spectroscopic survey of nearby galaxies. This is a very major undertaking at the time at Palomar that was initiated by Alex Filipenko while he was still here as a student working with Wal. And then later, for the next 10 years later, became part of my thesis at Berkeley. We finished the analysis and publications. It was a very ambitious survey at the time. The goal was very simple, to obtain the best possible optical spectra that you can get at the time, given the telescope and facilities, of the 500 brightest galaxies in the northern hemisphere. There were many goals, but one of the primary goals had always been to try to very carefully quantify the incidence of AGN activity in the nearby universe, and of course, by implication, black holes, because AGNs derive from accretion into massive black holes. Of course, they knew at the outset this would be a tough game, because if there is any AGN activity, it's likely to be very weak, because by the present-day universe, there isn't much accretion or star formation going on in the centers of galaxies. But we knew from Don and Lindenbell's suggestion in 1969 that there ought to be remnant quasars lurking in the centers of nearby galaxies. So they obtained very high-quality spectra. Here is a selection of Sept galaxies from the Palomar survey. And you might be amused to think that these are all Sept galaxies. You all recognize famous object like NGC 4151, very prominent featureless continuum, very broad, strong emission lines. But as you go towards fainter and fainter objects, the broad lines disappear to the point where even the narrow lines become very challenging to measure unless you have a very high-quality spectra and a way to model the underlying stellar continuum that dominates the light, even within a 1 or 2 arc-second slit. Okay, but I can assure you these are Sept nuclei. So there were two primary objectives from the outset. One was to have a survey that was deep enough to be able to detect broad H-alpha emission. Broad H-alpha is expected to be the brightest permitted line in the optical region. And here it is. You wouldn't notice it easily from the original spectrum, but after very carefully modeling the underlying bulge light and modeling the very complicated line profiles, there indeed is a broad emission line component. Of course, this is a hallmark feature that distinguishes quasars and Sephirts, stuff moving around at thousands of kilometers per second. In case you're not convinced by this, most of the broad line candidates from Palomar have subsequently been surveyed with much smaller apertures afforded by HST. Here are 3 spectacular examples. Without any stellar subtraction, because it's not necessary, we detect not only extremely broad emission lines, but they're double-peaked and asymmetric. This is the distinctive kinematic signature of the outer regions of a relativistically rotating accretion disk. This type of broadline emission was detected in roughly 25–30% of the sample. The majority do not have obvious broad lines and dominated by narrow lines. And the objective here is physically very straightforward. In the optical, these dominant recombination and forbidden lines come mostly from photoionization, and we can distinguish by their relative intensities whether the central ionizing source is coming from an O star, okay, which is the bottom object in H2 region, or whether it's coming from the spectrum of an accretion disk, which has many more high-energy photons. Okay, that is the basic idea. You can codify this in the so-called Baldwin-Phillips-Turlevich diagram. So we plot ratios of certain diagnostically sensitive lines. This is O35007, which is a high ionization line, and various low ionization lines. And the upshot is that O stars produce these yellow points, which lie on a locus which is very distinct from the other points, which are produced by various types of AGN accretion. Okay, so we use these line ratios essentially as a thermometer for the shape of the ionizing spectrum. This was back in ancient days before large surveys like Sloan. Now we can populate these diagrams with hundreds of thousands of objects. The basic results, however, have remained qualitatively unchanged. In fact, it's amusing to note that the Palomar survey, even though it's predated by at least 2 decades and is orders of magnitude lower in number, in fact, is 2 orders of magnitude more sensitive than your typical Sloan spectra. So some things simply don't get better with time. That's a message for graduate students, why you should work hard on your thesis. In case you're still not convinced that these objects have much to do with accretion, in the last decade, we've spent considerable time getting multi-wavelength data at high angular resolution, for example, hard X-rays from Chandra, where we detect these compact hard X-ray cores in basically 75 to 80% of the sample. Most of the survey has also been surveyed at arcsecond and in some cases even milliarcsecond resolution with a VLA and VLBA and other VLBI networks. And invariably, about 80% of the case, they have a compact, flat spectrum, in fact, non-thermal brightness temperature radial cores. They really are the base of jets, okay? Now, they're not just scaled-down versions of more luminous things. I don't have time to discuss this issue at all, but one of the very rich things that came out of this survey is that we're actually learning fundamentally new and different phenomena associated with accretion flows in the generation of jets. The vast majority of the objects you can see are highly, highly sub-Eddington. So this is a Sloan sample. These are the Palomar sources of different kinds. They go down to 10 to the minus 6, 10 to the minus 7, 10 to the minus 8 of the Eddington rate. And in this regime, as some of the specialists are aware, you begin to enter so-called radiatively inefficient accretion flows. There's very interesting analogy with the different states of X-ray binaries. I just came back from a meeting in Italy just a couple of days ago where this was the entire focus of the meeting, is to draw analogies between black hole accretion on all mass scales. But that's not the main focus of this talk. What I want to say is what we have learned from the Palomar survey concerning black hole demographics. And the upshot is that we detected AGN-like signatures in more than 40% of the entire 500 galaxies. But if you focus on the early types, the things that were prominent bulges, the SBs, S0s, SAs, and ellipticals, in fact, the detection rate is nearly 75%. You realize, of course, this is a firm lower limit on the incidence of black holes, because, of course, there are things that lie below a detection limit. Okay? So long before HST started detecting black holes dynamically, we already basically suspected that essentially 100% of bulges in nearby galaxies contain black holes. But the game really only took off seriously for most people when dynamical detections of black holes became possible. The most famous case remains, and the best studied case remains, the galactic center, where proper motion measurements over more than 15 years by Andrea Ghez at UCLA and Reinhard Genzel and MPA have managed to track the motions of the stars and model them and infer that there's 4 million solar masses in the center. That is not the important point. The important point is all of that dark mass is jammed into a light weak, right? So that the inferred mass density is so extraordinarily high, greater than 10 to the 12 solar masses per cubic parsec, that essentially all astrophysical alternatives to a single collapsed object can be reasonably ruled out. Another very important early development, more than 15 years ago now, came from the radio community, where they discovered this famous mega maser galaxy, NGC 4258, where the maser spots define a almost edge-on sub-parsec scale accretion disk that traces an almost perfect Keplerian rotation curve. In this situation, you can derive the mass extremely simply and very accurately, and again, confine it to a very tiny volume because this is VLBI resolution. On the other hand, I think the subject really only took off in the sense of causing a major impact on extragalactic astronomy in general, really with the advent of HST, okay? When it was, now we're actually able to routinely survey large samples of nearby galaxies. In the early days, the observations were relatively primitive. This is M87. There's a H-alpha disk of ionized gas. There's large velocities. Okay, you infer a large binding mass. And then increasingly more sophisticated observations, once there was a long slit spectrograph, STIS that was installed, allowing detailed maps of the spatial distribution and velocity field of the gas, allowing more accurate measurements of the central mass. At the same time, people were fully exploiting stellar kinematics, not relying on the gas, but using the stars in the bulge. Most of the work came from a collaboration known as the nuclear team. In fact, there are several members here in the audience, where for several years we've used HST very heavily to systematically survey many nearby bulges. And the results were at first very surprising. We were finding central dark objects consistent with black holes, and then it got kind of boring. We kept finding them, okay? And that is, in essence, the answer, is that black holes were in every bulge. This was one of the early results on demographics. And so it took a long time, but basically we confirmed Lindenfeld's prediction from 1969 that the centers of big nearby galaxies ought to contain dead quasars. We eventually reached a point where we had enough objects to make a scatter plot. We plotted the mass of the black hole versus the mass of the central bulge, and quite unexpectedly we found that there was an almost linear correlation. Now, this result in hindsight was already suggested in 1989 by Alan Dressler based on very little data, but it was very prescient that he actually made the suggestion, and then Cormandy in the 90s also suggested, but really took the large samples from HST for Magorian to basically have his name immortalized thereafter. Okay, so this is the famous Magorian relation. 2 years later, we found a correlation that is even more infamous, the so-called M-sigma relation. The mass of the black hole correlates very tightly with the velocity dispersion of the stars in the bulge. I'm not going to talk much more about this. I'm going to give you some updates because later speakers, I think at least Phil Hopkins, if not others, will discuss the physical implications and perhaps physical origin of this correlation. But suffice it to say, this is the paper that launched 1,000 other papers and hundreds of careers, right? And in fact, it really was a genesis of many modern concepts in galaxy formation, such as AGN feedback and black hole galaxy coevolution. People started taking it very seriously once they realized that this very small scale communicates with a very large scale. So over the last 10 plus years, we've basically come to accept a number of facts that are relatively uncontroversial by now, okay? To the point that you might call it some kind of standard paradigm. The first, as I said, is that all bulges contain black holes. And the mass of the black holes that are measured correlate very strongly and roughly linearly with the mass of the bulge. The ratio is tiny. It's only about 0.1 to 0.2%. The M sigma relation has a slope of 4. And it's widely believed that the M sigma relation is somehow more fundamental, more physically fundamental than the correlation between masses, because the intrinsic scatter has been said to be smaller. With the existing samples, there was no strong evidence that there is any dependence on mass or morphological type. In the last few years, there's a lot of work on trying to track whether these scaling relations evolve with time. And there's been claims that there's significant evolution even with at redshifts as recent as 0.5, and by the time you get to the high redshift quasars, that the mass of the black hole relative to the mass of the bulge may be larger by nearly an order of magnitude compared to the local value. And again, the theorists invoke AGN feedback as one of the primary agents to effect these correlations. I'm now going to give you a very quick rundown of some very recent developments. I'm going to be very, very brief because most of these details are covered in a new annual reviews article I just wrote with John Cormandy, which is on AstroPH. I'm just going to give you the briefest of the highlights. There have been substantial quantitative as well as qualitative changes to the standard picture. In terms of data, the most impressive thing has been the deployment of adaptive optics-assisted spectrographs on 8 to 10 meter class telescopes, where you no longer need HST. In fact, HST could not touch the subject. Okay? That is to search for dynamic evidence for black holes in the brightest cluster galaxies, such as Coma, where in this particular case of NGC 4889, Makano et al. Announced that it has a black hole of 20 billion solar masses. Okay. This is something that HST couldn't do because the surface brightnesses are very low for these massive ellipticals, and HST is a 2-meter telescope. Very important contribution has now come from the radio community, where after more than 15 years hiatus, they now have a new sample of water masers. Here's a sample of 7. I'm told there are roughly a dozen forthcoming. This is a very important byproduct of a cosmology project to use by an NRAO, spearheaded by Fred Lowe here, in fact, sitting in the front row, to use masers to measure the Hubble constant. And as a byproduct, they detect these, again, almost perfectly edge-on sub-parsec scale disks, which are rotating very regularly, so you can obtain very accurate and very simple masses, especially in a regime where previously there had been very few reliable measurements. These are late-type galaxies, generally. There are other important improvements to the sample, which I don't have time to discuss. The bottom line is, once you clean the sample and once you include the latest data, these are the correlation diagrams between the mass of the black hole and the mass of the bulge and the velocity dispersion of the bulge. I include here only elliptical galaxies and so-called classical bulges. For those of you who are not familiar with this terminology, classical bulges, you can think of them as tiny ellipticals. These are objects that are old, that formed a long time ago at high redshift, presumably with a relatively short time scale and with lots of dissipation. Okay, not necessarily major gas-rich mergers, could be cold flows or whatever, but involves lots of gas. Okay, and these objects define very tight correlations. In fact, the intrinsic scatter is essentially comparable for these two diagrams. On the other hand, the so-called pseudo-bulges, these blue points, these are objects that probably did not involve major mergers, that formed over a long period of time, still in fact undergoing star formation, and likely simply involved internal secular processes like angular momentum transport by bars and whatnot, really do not define any tight correlation at all. Okay, these are the blue points. Okay, so what are the implications for the M sigma relation? Well, first of all, the slope is marginally larger than 4. It's about 4.4. The scatter is about 0.3 dex. The more surprising result, if I can advance the slide, concerns the correlation between bulge mass and black hole mass. The scatter is identical. It is not true that M sigma is, has smaller intrinsic scatter. In fact, it's identical. The correlation is formally greater than unity. It's steeper than unity. It's roughly 1.2. And the normalization has increased by about a factor of 4. rather than 0.15, it's really about 0.5. But because the slope is greater than unity, in fact, the ratio is not constant. Okay? In fact, it's a function of mass. Let me very quickly go over just a couple of points regarding AGNs. I'm not going to belabor this because Juna Kohlmeier and Brad Peterson, I'm sure, will cover this at much greater depth. But one of the consequences of the discovery of the M-sigma relation and the realization that AGN feedback may be very fundamental to galaxy formation is that it's really caused a major renaissance within the AGN community. I mean, for the first time in many years now, you know, cosmology meetings actually think that Bialak objects are cool. That's never happened when I was a grad student, okay? Okay? Because jets are now just a panacea to solve all your problems and catastrophes and whatnot, okay? It's true, right? Apparently. In any case, what over the years now we have devised are now secondary methods to estimate black hole masses using so-called the Virial technique, essentially to AGNs with broadline spectra out to essentially arbitrarily high redshifts, right? We can use optical lines locally, UV lines at high redshift. And it's said that the uncertainty is about a factor of 2 to 3. Okay, I won't discuss this much more in this talk. Let me just simply mention two interesting applications. The first is the discovery and then systematic characterization of low-mass black holes in very low-mass, late-type, and even dwarf galaxies. Roughly 10 years ago, two such objects were known, and only two. They both trace back to Sargent and here at Caltech. Okay? The first is a very famous face-on spiral galaxy that was discovered by Alex and Wall in the Palomar survey, NGC 4395. And the second is also an equally bizarre object. This is formerly a spheroidal galaxy. So even though it looks like a football, it really is not related to elliptical galaxies. It's much more physically related to dwarf galaxies. And both you can see, and that was originally studied by Daniel Kunth and Walt Sargent and followed up by Aaron Barth. They both have Sept spectra. They have all the trappings of genuine AGNs. But those are the only two objects known, and they have black hole masses of roughly 10 to the 5 solar masses. It took the statistics of Sloan to really bring the subject to fruition. This was the thesis work of Jenny Green, who analyzed hundreds of thousands of spectra from Sloan, calculated a mass function, and then identified a sample of more than 200 sources with black hole masses formerly less than 10 to the 6 solar masses. And these objects truly are amazing. So we've imaged most of them with HST. Out of a sample of roughly 200, only one has a fairly prominent bulge. Roughly 2/3 of them are these very late type spirals, very similar to NGC 4395, and about 1/3 are these spheroidal-like galaxies, these dwarfish galaxies. Okay, so these are really low-mass black holes in very primitive-looking galaxies. So you might view them as very interesting laboratories to study what the analogs of the seeds that made supermassive black holes might have been back in the redshift 10, 20 era. Okay, so these are very local examples that are very important in that context. And finally, in the last just few minutes, I'm going to wrap up. You can apply these Virial techniques also to very high redshift quasars to study the possible evolution of these scaling relations with time. So what I've compiled here is a list of all available, reliable, high redshift quasars. These are redshifts of 2 to up to including the redshift 7 object that have estimates of the Virial black hole masses and also some dynamical information that allows me to infer the host galaxy mass. And the first astounding thing I didn't expect is that there should be any semblance of a correlation at all. Okay, so I didn't do any formal analysis. You can just look at it. Okay, and of course there's significant uncertainties on the x and y axis. So in fact, the intrinsic correlation must be tighter than this. Okay, so there is something even at these very high redshifts. These are optically revealed, largely unobscured quasars. On the other hand, if you look at type 2 quasars and so-called submillimeter galaxies, which are these red and orange points, you can see that they have nearly similar stellar masses. These are huge masses. These objects are destined to become present-day giant ellipticals, right? They're almost as massive as they'll ever become. But their black holes, if you can trust these numbers, are 1 to 2 orders of magnitude below this locus. What I would like to know for the theorists in the audience is how do you go from these objects to those objects, and some people say you accomplish that within 200-300 million years, grow the black hole by factors of 10 to 100, and know to stop right there and not go above. Okay, maybe this is AGN feedback in action, but I find that fascinating. And by the way, after a short while, less than 1 billion years, you have to blow away all the gas, quench the thing, and make a red nugget. Okay, for those of you who know what that means, that's what dominates the extragalactic imagination these days. On the other hand, if you go to lower redshift objects, below redshift of 2, most of these are lower mass black holes. These are the things that Gunther was talking about that you see in the X-ray background. They live in disk galaxies. Okay, these are spiral galaxies or just generically later type galaxies, and you can see that there's hardly any correlation whatsoever. So even at these high redshifts, and these are by selection actively growing black holes, the pattern already mirrors what we saw locally for the inactive black holes. Okay, so what I'm suggesting is these are the ellipticals and classical bulges, and these are the pseudo bulges. So already these trends are already in place. And indeed, if you compare this distribution compared to the local relationship, okay, this dash point, you would conclude that there is significant evolution. This is what's been talked about for many years now, okay, that these objects tend to lie above the local relationship. But that's because people have been using the classical normalization, but if you use the revised 0 point that I just described earlier, which is a factor of 4 higher, in fact, the amount of evolution at moderate redshifts essentially disappears altogether. And at high redshift, there indeed still is an excess, but it's a much more reasonable amount. It's only a factor of 2 to 3. That is entirely to be expected because these massive galaxies will double in mass, roughly speaking, right, by the time they reach redshift 0. So there's, I think, no serious problem in having these objects converge to the local normalization. So let me finish with a summary of the recent updates. Okay, so now we've extended the black hole mass function from as low as 10 to the 4 and to greater than 10 to the 10 solar masses by 6 orders of magnitude. It remains the case that all bulges contain black holes, but it is not the case that all black holes require bulges. Those very late type galaxies, those are not bulges, those are disks, okay? And yet they have central black holes. The correlation between black hole mass and bulge mass is formally slightly larger than unity, and the ratio of black hole mass to bulge mass is roughly 0.5%, it's about a factor of 4 on average, higher than before. M sigma goes marginally larger than slope of 4. And the slope, the intrinsic scatter of these two scaling relations are effectively the same. It's about 0.3 dex. However, these relationships are tight only for the elliptical galaxies and the classical bulges. The pseudo bulges really do not define any intrinsic relation whatsoever. It's very interesting when you look at the population of high redshift AGNs and quasars that this type of scaling relation was already in place in the high redshift quasar population, okay, at redshifts of 2, 4, and even 6. There is a mild amount of evolution by maybe factors of 2 or 3 for these massive black holes that live in quasars. What this means for AGN feedback ideas, I will be very interested to hear subsequent talks, but I think these new observations offer some very important new insights. So with that, I'll end. Thank you very much. Well, I would be the first to share your concerns, but this is what we got now, Meg, right? So I chose to plot them in this diagram, but many people write papers that use exactly the same technique to study black hole mass functions. I agree. There are many ways that the black hole mass measurements could be wrong, but I think most of those effects would tend to, make this thing worse I'm sorry, make the intrinsic relation better, not. So I'm just astounded that there is anything at all, okay? And similarly, the x-axis is very problematic, okay? I didn't tell you the dirty details of what went into it. But I think, for example, ALMA, right now and in the near future, can use molecular lines to really get velocity fields and really properly measure sizes to get dynamical masses, okay? So I share your concerns, but this is what we can do at the moment.
See, Maarten?
There was a claim of a very big black hole in a small galaxy in the home cluster. There's a process cluster.
Yes, yes.
Do you believe that?
Yes, yes. So I have no reason to independently doubt the dynamical analysis. That's not my area of expertise. But if you take it at face value, there is a nearly 20 billion solar mass black hole in a galaxy. For those of you not familiar, that seems to be a factor of 100 or at least tens under massive. I think there are two possibilities to explain that. Okay, the prosaic explanation is that the galaxy has been significantly stripped. So in fact, the galaxy is much larger than it originally. The Perseus cluster is a very violent environment. That's where NGC 1275 is. Okay, and next to M87, we have another example, M87b. In fact, that basically is qualitatively the same. The more interesting explanation is that the 1277 may be a remnant of the so-called red nuggets at high redshift. So imagine these quasars just shut off the gas, the black hole is frozen, but also freeze the stellar mass by not allowing it to merge and grow and whatever ellipticals do. Okay, so statistically, that should happen some of the time, right? I mean, there are I wonder if that object is such an example. But I'm told that they have a sample with several more such candidates. So I think with one, it's difficult to generalize at the moment.
Yeah, go.
So for the pseudo-bulges, sigma may not be, or mass may not be a particularly good tracer. If say what the black hole really cares about is the total potential at the center of the galaxy. I can believe that for classical bulges, the bulge dominates that. But for pseudo-bulges, that may not be true. I know you've looked at, is there a better correlation for the pseudo-bulges using more information on the galaxy? Or?
So, we looked at the stellar mass, right? I mean, and these are real, honest-to-goodness stellar masses. We just didn't take the luminosity and some average mass-to-light ratios. And what I showed you with those two panels, one was with stellar mass. So the stellar mass isn't any better. And correlation with larger scale properties like the dark matter halo or rotation velocities are also not any better. So, now it's possible that within every not possible, it's logical that essentially every bulge is effectively a hybrid, right? I mean, even ellipticals are forming stars at some rate, and classical bulges have, so it's a matter of degree. So it's entirely possible that the things we call pseudo-bulges have, in fact, embedded within them some smaller classical bulge component that we've yet to disentangle. Okay, and of course, the sense of that might, in fact, be to shift it back on the relation. That's just a pure speculation. Okay, but at face value, the two classes of objects are qualitatively and quantitatively very different.
Okay, Donald, last question.
Would you like to tell us anything about M33?
I have no new information to report other than that's, in fact, one of the few late-type galaxies. So M33, for those of you who don't know, has a central star cluster that's very dense. It's similar to Omega Centauri or G1. Okay, that's not atypical. 80% of late-type spiral galaxies have such central star clusters, and some of them have black holes, like the ones I showed you. M33 notably doesn't, and there's the original HST measurement is still valid. It has an upper limit of 1,500 solar masses. And there's also no evidence for any other signs of accretion in terms of X-rays or radio emission. Okay, so it's definitely the case that there are nuclear star clusters, and perhaps even the majority of them do not have any evidence for a central black hole. And the reasons why some do and some don't are fascinating. I think it's a very interesting theoretical problem.
Okay, well, let's think through this again.